So once again, the kernel matrix is kind of the covariance matrix of the new mapped space, yeah, that we get if we apply the mapping phi to our data set. Yeah? So that's what we said here. Yeah? So the kernel matrix is nothing else than applying the mapping to D transpose times applying the mapping to D, yeah? Which is somehow the covariance matrix. This is the covariance matrix of the original data set, and this is the covariance matrix of the transformed data set. Now let's we applied SVD on the covariance matrix in order to get the eigenvalues of the original data set. So if we do that now with the covariance matrix of the transformed data set, we'll probably get, yeah, exactly the eigenvalues and the eigenvectors of the transformed data set after the mapping. And that's what we actually get. Yeah. So yeah, we just do that and we'll get exactly what we get before. So K will be so the covariance matrix will be decomposed into these two matrices, V and E, and of course the relationship to the relationship to the original the data set, to the transformed data set after the mapping phi is the same as before. So this transformed data set after the mapping, which we don't want to compute explicitly, yeah, but that data set, the transformed data set, can be decomposed into OSAT, yeah, and the relationship is as before. The A is the matrix of the eigenvectors, the V here, and the S squared is the matrix, the diagonal matrix of the eigenvalues. So S has the singular values of or the squared singular values of S has the singular values of this mapped data set. Yeah, so that is exactly the same as we had before. Yeah, the only thing is that now the original data is the mapped data, and the covariance matrix is the covariance matrix of this mapped data, which is the kernel matrix now. Yeah? So as I said before, V is still a basis of d-dimensional eigenvectors of this new mapping, of these new mapped space, and E has the corresponding eigenvalues for all these eigenvectors. The only thing now is that the rank may be not restricted anymore. Yeah. So typically we now get, since V has the kernel matrix and also of course the mapped matrix here, the mapped data matrix after the mapping here has n times d. So we typically get n eigenvectors and n eigenvalues. Yeah? So that is a little bit unintuitive on the first glance, but if you think about it and try to metabolize it, now the rank of this matrix here is not restricted anymore, so we typically get n eigenvalues and eigenvectors here. Yeah? And it may make sense, try to metabolize that. It may make sense if you think about that each eigenvector in A or V, depending on how you view it, A is V actually, is a linear combination of vectors in the mapped data space, yeah, and plus, yeah, a linear combination of the vectors of the transposed vector of the mapped vectors and the n eigenvectors in O here, yeah. And if you think about it, well, how can we know that? We can actually formalize that or formally prove that, because we have this decomposition of the mapped space, yeah, of the mapped data space, phi of D, into these three matrices here. Yeah. So if we add on both sides of this equation here the same term, specifically here O transposed, so on this side O transposed, so out of phi of D we get O transposed times V of D, and on the left hand side we also add O transposed, so we get O transposed times OSA transposed. So the right hand side, since O is an orthonormal matrix, yeah, so that is the identity again. So the right hand side comes down to SAT. So we have OT, O transposed times the mapped data space is S times A transposed. So if we try to get S on the left-hand side of the equation, we see that we have on the left-hand side still O transposed times the data matrix, and now S inverted, yeah, and on the right-hand side A transposed remains, and that is exactly the linear combination. So A, each eigenvector here in A, is a linear combination of O and one of and the vectors in the mapping space, yeah, times some scalar, which are the singular values in that case, yeah. So that is the relationship, and that may also makes it clear that yeah, we have n eigenvectors and eigenvalues instead of just d. And also that is important because now the mapping, we can still compute the mapping, but the mapping looks a little bit different now. So we can still compute the mapping of any object in the mapped space, in the transformed space phi of d. We can still transform it by the eigenvectors. Yeah, that's what we did before with the PCA. Yeah, so we used the v's, the eigenvectors, to transform the original data into a new data space. Yeah. Conserving the variation, and we can do that now also with these new eigenvectors v that we get here from kernel PCA, from the PCA on the kernel matrix. Yeah, so we can still do that by just computing this here. Yeah, and we can even do that without knowing the exact mapping. Yeah. As long as we know the kernel function, we'll see why just here in this equation here. So the kernel trick still works. We don't know how, the exact phi, so we don't need to actually compute the exact transformation, the exact mapping, in order to transform the data onto the new data space, onto the new axis computed by PCA. And why that works actually is, okay, so the mapping here is now a little bit more complex because we have, based on this relationship here, we still have here a linear combination of the v's here, yeah, of the v's and the transposed or the mapped data objects here, yeah. So and that comes down by just yeah, some kind of rearrangements to this one here, and you see on the right hand side. So that is how you compute the new representation based on the eigenvectors obtained by kernel PCA, and you see here that this transformation just needs to know about the kernel function, but not about the phi here. Yeah, so here we still need the phi, but here we don't have any phis anymore here. So we only have the kernels here. Yeah, and that is the nice thing here. So the kernel trick still works, meaning that we can transform the original data into, or map it onto, the eigenvectors computed by kernel PCA without knowing the exact phis here. Yeah, we just need the kernel functions, which rely on phi, of course, but just yeah, as we saw it before. Of course, we can also yeah, reduce the dimensionality if we only use k of the n eigenvectors in n. Yeah, as before. Before we had d eigenvectors in n. Now we have n in v. Sorry. Now we have n eigenvectors in v. And if we want to reduce dimensionality, we just take the first k. Yeah, that's fine. Yeah, so that's the basic idea, and we will have a look at an example, just that you know, if you're not confused yet, the inverse transformation into the original data space is not unique in general, so you cannot somehow compute the inverse transformation. If you do PCA, kernel PCA once, and do this transformation, you cannot recompute the original representation, but that's a different story. Yeah, so that is not, just that you know, yeah, shouldn't confuse you again. So here's an example. That is our original space here. Yeah, so something nonlinear happening here, and well, if you project the whole thing by PCA on the two first principal components, there's nothing one actually. So they're the same. We have the same data representation actually. Yeah. So if you do that with kernel PCA and take the two first components, yeah, so you get n components. I don't know how many observations are in there, but if you do that and map it to the first two principal components with a suitable phi, probably it's the same phi as we did before here. Where did we do it? Here? No. Yeah. Here probably. Yeah. Then we get and we map it to the first two components. Then we get this representation, and you see all of a sudden we can do fancy data mining shit. Yeah. And now if you try to inverse the transformation into the original space, it should look like this one here, but it's not unique, as I said before. So the back propagation, the back transformation is not unique. So that's why it looks a little bit different here. Yeah. So I hope you see it. Well, if you couldn't follow it, all the details, it's not so important. Of course, if you go through all of that, it's probably again deepening your expertise on PCA and SVD. But the main takeaway message of kernel PCA is that in things or in scenarios like this, of course with the correct or the right suitable kernel, that's a big deal, of course, trying out or finding the correct or suitable kernel function, but that's a different story. And of course you can try out different things, yeah. But anyway, if you find the right kernel or a good kernel, then you can transform the data from something which is very hard to comprehend from a data mining perspective into a representation where some patterns, some easy patterns can be easily found. Yeah. So, and of course that somehow transfers to some much more complex patterns in the original space. Yeah? So that is the downside, that if you find those patterns here, you can try to transform it into to the inverse transformation to the original space in order to understand the patterns that you get here. Yeah? So that is the downside, that these patterns here in this kernel PCA projection are probably very, very hard to comprehend, very, very hard to understand and understand. So you probably want to transfer it back, but that's very often not absolutely possible. Yeah? So the interpretation of these of these patterns here in the kernel PCA space is very, very hard very often. Yeah? But that's just one downside. The good point is that you make some you can find some really, really complex patterns in the original space by doing or by applying a suitable kernel function. But once again, the big thing is how to define the right kernel, how to define or how to find the suitable kernel. Okay, so that was kernel PCA. Pooh.